Good afternoon and welcome to Expeditions and Experiential AI with Silvio Amir, hosted by the Institute for Experiential AI. Today we are pleased to discuss large language models as data interfaces for health applications. Silvio Amir is a core faculty member at EAI and assistant professor in the Khoury College of Computer Sciences. His research develops natural language processing and machine learning methods for personal and user-generated text, such as social media and clinical notes from electronic health records. Silvio earned his doctorate from the University of Lisbon, conducting part of his doctoral research as a visiting researcher at the University of Texas in Austin, as well as right here at Northeastern University. Please join me in welcoming Silvio Amir.
Thank you so much, Liz, and welcome everyone. So I hope you can see my slides. So the title of my talk is Large Language Models as Data Interfaces for Health Applications. And so I'd like to start just by taking a bird's eye view of how natural language processing has evolved since the advent of large language models, since this technology has been quite transformative, has kind of taken over the way in which we do NLP research and applications these days. And in particular, in the last 5 years, we've been through a couple of different changes in paradigm with the advent of the transformer architecture. We began pre-training these models with large amounts of unlabeled data, and that kind of brought about this paradigm of simply pre-training these models and then fine-tuning them for specific applications. And this was mainly driven by architecture such as BERT. Then we moved to pre-training at scale the decoder side of the transformer architecture, which is pre-trained to predict the next sentence in a string of text. And it turns out that if we scale these models enough, with both in terms of size of the model and size of the data, we can then do in-context learning, where we simply prompt the model to solve different NLP tasks without needing to adapt the models directly to the data distribution that we care about. And this then led to approaches where we kind of fine-tune these models with instructions such that they are better at answering prompts. And this led to further improvements in how easily these models can be transferred for various downstream applications. And then there has been a lot of interest in turning these models into assistants and dialogue agents. And this usually entails a final step where we use reinforcement learning from human feedback to train the model to give the model higher probability of generating outputs that are preferred by humans. In terms of applications of these language models, aside from these chatbots, kind of the magic sauce now is this idea of fine-tuning models with instructions. And in particular, the model that we've been exploring in research is the Fluenty-5, and here we can see an example of this idea of instruction fine-tuning, where we essentially reframe a lot of NLP tasks as prompts and answers to these prompts. In particular, this idea of chain of thought prompting has become quite popular, as it has been shown that this allows the models to give better answers, and the idea here is that the models need to explain their quote-unquote reasoning, and this leads to better responses by the model. So kind of the idea now is, let's scale up the amount of instruction fine-tuning data sets. Now these models are trained with thousands of tasks, and we find that in this regime, the models can then generalize to unseen tasks using kind of this approach. And so kind of the trend has been to have a single generative model to rule them all. We have a single model that can solve all sorts of tasks. Turns out that these models can solve a variety of NLP problems with minimal supervision. They can help users perform real-world tasks when they are further aligned with human feedback. And this allows users to engage with these models using dialogue. The models can answer questions, help users writing emails, help students do their homeworks. They can help programmers write code. And so all these capabilities are wonderful, but they are also kind of raising the question of whether these models can significantly displace jobs, and in particular, knowledge workers' jobs. And it's unclear what the final impact of this technology will be as it keeps evolving. But it seems that we are already feeling some of the effects of the availability of these types of technologies. There are reports that AI eliminated around 4,000 jobs in the May report. IBM says that it is considering replacing almost 8,000 jobs with AI, and so this is quite concerning. On the other hand, we know that these large language models can generate false and harmful outputs. They suffer from hallucinations. They can generate toxic and biased outputs. And for example, Galactica, one large language model that was trained on scientific literature, has been found to generate quite harmful outputs, things like generate an article about the benefits of suicide, or a research paper on the benefits of eating crushed glass, where the model says that eating crushed glass has been shown to lower stomach acidity much better than say bran wheat. We also see that in this rush to release chatbots for healthcare, we can see that models are still quite biased. For example, these are two different chatbots that have been released recently that have been trained on interactions between patients and doctors. And so if we ask a question about experiencing painful urination and we ask for the cause, we can see that one of the models seems to assume that I have a prostate, while the other one seems to assume that I have a vagina. And so it's questionable how useful these models are in and of themselves, and how much harm can they cause if they are not under the guard of professionals and experts. So these two examples are from models that have been used in research, but we have also seen recently, this was last week, that the National Eating Disorders Association basically fired their entire helpline, a set of workers from the helpline, I guess because in response to the fact that they have unionized. And so they fired all these workers and replaced them with a chatbot. And a week after, they had to shut it down because it turns out that the chatbot was recommending it was giving harmful advice to patients. Another recent example was this lawyer that used ChatGPT to do his legal research, and then it turned out that some of the cases that ChatGPT mentioned were basically fake, and so this was very problematic. So kind of the takeaway here is that I don't think that it's a good idea to release these models and let them work by themselves, because they can be quite harmful and problematic, particularly in kind of consequential domains. And so, in my view, I think our efforts as researchers would be best invested in figuring out how can we use large language models to empower rather than replace human experts. And in particular, for knowledge workers and experts in general. Often they need to derive insights from large and complex data sets and use this to improve data-driven decision-making processes. And so one approach, an idea that I'm excited about is whether we can use large language models as conversational data interfaces. So the idea is that we could use these fluency ability to generate fluent dialogue and text to help us understand complex data sets by retrieving key pieces of information, and in particular from unstructured data such as text. And hopefully this will allow experts to then, another consequence of this would be the ability to answer complex questions about the data. And so because these models suffer from these tendency to hallucinate, the answers must be grounded in factual data, which means that we need models that can generate both abstractively, and you know, these models are pretty good at generating text by themselves, but we'd also would like these models to be able to extract specific pieces of information and generate responses that are based on factual instances of data. And so this raises the question is of whether we can frame extraction tasks as generation. And so in this talk, I'm going to talk about some recent work that we've been doing in using large language models for relation extraction and for structured evidence inference. So some potential applications for this type of approach are, for example, for evidence-based medicine. We could help practitioners understand what, for example, is the most effective treatment for a given condition based on randomized controlled trials. Public health experts could utilize these types of data interfaces to understand what are the main health concerns of a given population based on large repositories of social media data, and healthcare providers could use these tools to aid in diagnosis, for example, to understand if there is any evidence that a patient may be suffering from a given condition that the physician might suspect. And so I would like to start by looking at the task of relation extraction. So the key idea here is, or the goal is to identify entities, their types and relations in text. For example, even a sentence like the diagnosis of hypothermia was delayed until it was apparent for several days, but resolved with the discontinuation of risperidone and continuation of clozapine. We may want to take a snippet of text like this, maybe coming from a clinical note, and we want to find instances of drug adverse reactions. And so the idea here would be that we would identify both the effects and the drugs, and then we would try to classify whether the drug and the effect have an adverse, whether the drug is an adverse effect. Another more classical example of relation extraction is to extract named entities and their types from text, things like persons, locations, and organizations. And so the first step would be to identify these entities and then classify the relationships between these entities. So one thing to note is that these entities can appear, can be part of multiple different relations. And so this is an instance of a structured prediction task, where kind of the goal is to produce this kind of table format where we have these entities and their relations. So the typical approach to this involves a pipeline where we first use a model to identify the entities on a given piece of text, and then we use a second model to classify the relations between pairs of entities. This is not ideal because when we use pipeline approaches, the errors of the different components of the pipeline may kind of compound. And so more recently, people have been exploring kind of end-to-end approaches where we take a snippet of text and we produce the entire structured output. So in recent work, we decided to look at this problem from the standpoint of conditional generation using a large language model. And so here we essentially take the structured outputs, we linearize them, meaning we convert them into strings. These strings consist of tuples, lists of tuples. And so given the input text, the model needs to generate these linearized outputs token by token. So in practice, what we do is we construct a few shots prompts with several examples of texts. We have a prompt that asks the model to list all the drug and adverse effect pairs. We pass the text, and then we pass the linearized target outputs. And then we pass a last example and ask the model to generate the corresponding output. So one challenge on leveraging this approach is that because these models can generate text freely, the outputs that they generate can be non-conforming to the references that we have, and moreover, the models can generate instances that are semantically similar to the references, but they have different strings, essentially different tokens. And so they are lexically different, but they mean the same thing. Moreover, these models can find relations that are actually valid, but are not part of the references of these examples. And this makes it very difficult to conduct automatic evaluation based on some gold references. And so in our work to sidestep this, we resorted to human evaluation. And here are some examples of these erroneous outputs. So here on the top left, on the ADE case, we see that the reference was actually wrong. It mentions a case that is not present on the input, but the model finds an instance that is actually on the input text, but it was not part of the reference. And so this is one of these kind of false positives. On the bottom right example, we can see that the reference here is that Charles Guiteau killed the President James A. Garfield, but the model generates shot by. And if you look at the input, that's actually what the text mentions. It says that James A. Garfield was shot by Charles J. Guiteau. And so these are some of the complications that we found on trying to tackle this problem using the generative model. So in terms of performance, we found that using GPT-3 in a few-shot approach slightly outperforms the previous state of the art. However, we tried to improve upon this performance by augmenting the prompts with a chain of thought type of explanations. Essentially, we augmented each input with a simple explanation for the output. And it turns out that this significantly improves performance, but notably, it also reduces the amount of these non-conforming outputs. In terms of performance, using a few shot with this chain of thought explanations with GPT-3, we see a slight increase in performance. But what we ended up doing was to use GPT-3 to generate these explanations at scale. Again, we use prompting. We gave the model a few examples of inputs, the targets, and the explanations manually written. And then we asked the model to generate explanations for the remainder of the data. And by doing this, we amassed a new data set that we used to actually fine-tune a quantified model, a much smaller model. And with this, we end up significantly outperforming both the both the state-of-the-art model at the time and the approach of using GPT-3 with few-shot. So this is encouraging, and so we then moved on to experiment with this type of approach, but in the context of evidence-based medicine. So in evidence-based medicine tries to use the best available scientific evidence to support medical decisions. And basically uses evidence from randomized control trials and systematic reviews to inform these decisions. However, there are new reports being published daily, and so it's difficult to stay up to date. And so there has been interest in approaches that can kind of automate the process of inferring relevant information from these randomized control trials. In particular, Trial Streamer is this project by one of our colleagues at Northeastern, Byron Wallace, that ingests newly published evidence and then uses a set of machine learning models to extract relevant information from these reports. In particular, things like what are the populations being described in the studies, what are the interventions being analyzed, and what are the outcomes being measured. And so these elements, the population, the interventions, and the outcomes are key elements for well-formulated clinical questions and what characterizes randomized control trials. This interface provides all this information, also provides a small summary of the paper, kind of like the punchline. But one thing that this interface does not provide is what was the effect of the different interventions on these outcomes. And so the way to move forward or to add this information is the goal of this proposed task developed and was proposed in 2019 by Byron Wallace and other colleagues. And the idea is that we can have models that go over randomized control trials. These trials can describe multiple populations, interventions, and outcomes. And the goal here is to extract all the tuples that all the intervention, comparative, and outcome tuples. And then for each of these tuples, infer what are the actual effects of the interventions on the outcomes and extract evidence to support that assertion. Here's an example of an abstract and the extracted information. So the intervention was these oral zinc sulfide capsules. The comparator was placebo. And there are two outcomes being discussed here. One is cutaneous warts. The other is recurrence of cutaneous warts. And we can see that the proposed intervention had no significant difference on these outcomes. So again, we asked whether we can frame this task as language generation. So the idea is that we would go from the RCT abstract. We would test this to a model that would generate linearized outputs describing the interventions, the comparators, the outcomes, and the findings along with evidence. So again, we linearize the targets, and these are examples from the abstract that I showed before. So again, for this task, the state-of-the-art was based on a pipeline approach where three different models were used. One to extract the PICO elements, Another one to link these to mesh codes to make sure that the references correspond to the actual Pico elements. And then from there, another third model would then infer the labels, whether there was a significant impact, whether the intervention increased, decreased, or had no impact on the outcome. So our approach was to replace this whole pipeline with a large language model. Specifically, we fine-tuned FLAN-T5 on pairs of abstracts and linearized targets. And we find that this approach significantly outperforms the previous state-of-the-art, which was this Eli model. We then utilize this fine-tuned FLAN-T5 to process the entire database of trial streamer to produce these structured summaries of findings, which can allow then EBM practitioners to more quickly find evidence about the efficacy of different treatments. So another application of this type of conversational interfaces is for public health experts. And so here we look at extracting medical claims from social media. So people use social media to discuss personal health and medical conditions, and specifically to ask questions, to seek advice, or to share their own experiences. However, given the unvetted nature of this data of social media, it makes it vulnerable to misinformation and disinformation. So we propose this novel task of identifying health-related conversations on social media, and we looked at specifically the Reddit platform. And so the task is as follows. Given a post, the goal is to extract fans corresponding to personal experiences, questions, or claims. And claims here are operationalized as statements that might reasonably be interpreted by the reader as implying a causal relationship between an intervention and an outcome. And then the second so these are two subtasks. First is identifying these experiences, questions, and claims. And then given the post and a claim, we want to extract the Pico elements, the populations, the interventions. And here we conflate interventions in the comparators because they are both interventions, and then also the outcomes. So we collected data from 24 subreddits, and we collected annotations from Amazon Mechanical Turk. Here are some examples of annotated posts. So we can see here the first example. I've seen a bunch of posts on here from people who say that glycopyrrolate suddenly isn't working anymore for hyperhidrosis. So this is a claim, and there's also a question at the end. Just wondering if anyone fixed it. So this is kind of the format of the data. So we also released a subset of this corpus for a shared task at Seminole 2023. We find that this is quite a challenging task, in particular the second stage where the goal is to find the Pico elements. And this is in part because it's this is a token level task, and so it's kind of there's this ambiguity of where to exactly place the boundaries between the spans. So an application that for this data set that we've explored in our paper was whether we could use this type of data to build models that allows content moderators to retrieve evidence that either supports or refutes a given medical claim found on social media. This could be useful either for content moderators, but also we could imagine having some sort of bot or agent that detects detects medical claims and automatically retrieves and evidence and presents this evidence to the users. So kind of the workflow is like this. We take a post from Reddit, we extract the questions, experiences, and claims. Given the claims, we extract the PICO elements, and then we use both information about the PICO elements and the post to then retrieve evidence from trial streamer that either supports or refutes the claim. So to retrieve this evidence, we used a dense passage retrieval model, which essentially works by encoding documents and queries as dense vectors, and then measures the relevance as the similarity between the query vectors and the document vectors. So this type of model is trained using negative sampling, where we use this loss function to ensure that queries that are related to documents, those vectors become closer, whereas the documents for queries that are not relevant become more farther apart. So a challenge here is that we do not have label data to train this model. And moreover, there is a mismatch between the language from social media and the language from randomized controlled trials. And so our approach was to derive some pseudo-label data where we essentially replaced the PIO elements from the claims with elements sampled from randomized controlled trials and then associated those. So the PICO elements from a given randomized control trial were then associated with the claim where the PIO elements were replaced with those of the RCT. And here's a couple of examples. For example, the last one says, I read that outcome could be due to population. And so we just go on trial streamer. We take RCTs that discuss ankylosing spondylitis, and then we replace the outcomes with the populations. And so we do this for a large number of examples, and we use this then to train our dense passage retrieval model. These are some results. They're not super important for this conversation, only to note that BM25, which is kind of the back and forth approach, canonical back and forth approach for information retrieval, performs much worse than this dense passage retrieval model trained on this data. However, this is not a fair comparison because this model was actually trained on this data. And so to better measure the ability of this model to retrieve relevant information, we enlisted medical doctors and we requested relevance judgments from 100 claims and 10 abstracts per claim, retrieved with our proposed model, this red hot DR, and a pre-trained dense passage retrieval model that is publicly available. And so here the upshot is that this is quite a difficult task. We can see that using our training data significantly improves the ability for the model to retrieve more relevant abstracts and less irrelevant abstracts across the across all the cutoff points. And so finally, I'd like to talk about this final application, which is to help diagnosis help experts in making diagnosis. And so here, what we see as a use case is a physician at point of care, maybe looking at a patient, or maybe looking at some exams or diagnostics, and may have a potential diagnosis in mind. And so here we would like to use these models to retrieve evidence that would support a potential diagnosis. Another related idea is whether we can use this type of model to suggest alternative diagnosis. that are supported by evidence from a patient's clinical notes. And so this is still a work in progress. We have teamed up with medical doctors from the Women's Brigham's Hospital, and we are trying to understand how is the best way to kind of elicit this type of, well, first of all, what are the best use cases for this type of approach, and how best to elicit this information from large language models. And so our initial experiments consist of, we're taking a Flanty-5 model, and we are essentially, at the first stage, we are trying to ascertain whether these models can retrieve this type of evidence without any supervision, without fine-tuning them. And so our initial experiments were based on constructing prompts and then seeing and evaluating whether the model is able to retrieve relevant information. So we are interested in also the use cases. Physician has a potential diagnosis in mind, for example, sepsis, and we would like to ask the model then to retrieve information about or evidence about this potential diagnosis. So if we just go ahead and ask the model, can you find evidence for sepsis and the set of clinical notes, what we find is that regardless of whether the patient is or is not at risk of sepsis, the model will retrieve something and will generate some response. And so to kind of counter that, we are envisioning now a two-step process where we first ask the model to read the clinical notes of the patient. And first, we ask the model to establish whether the patient is or is not at risk of developing sepsis. And only for the cases where the model is confident that the patient may indeed be at risk for sepsis, only then we ask it to retrieve evidence. So the preliminary results are quite encouraging. I will not show any quantitative evaluation today. We are still kind of fine-tuning this. Well, you know, we're still kind of understanding how best to operationalize this approach. But from our preliminary experiments, we found that the model is able to find relevant evidence. However, because the model was not trained specifically on medical data, we find that the model may retrieve pieces of evidence that are just too broad or that are not really pertinent in this specific scenario. For example, there are several risk factors for sepsis, but in the use case that we are envisioning, the doctor may have a kind of there's a specific context and the patient may be there for a specific reason. And so if the model just retrieves kind of generic evidence for a given condition, and sepsis is kind of one of those conditions that like there's a lot of different risk factors that may or may not be pertinent in this specific context. And so a couple of things that we try to do to improve this was to augment these prompts with known risk factors. But this led to really long prompts, and we found that the model ended up generating or just basically repeating a lot of the risk factors. And so now what we're doing is trying to generate more specific prompts, and we are asking our doctors what are some of the most relevant risk factors, or what are the risk factors that they would look for in a situation that is under analysis. And so We are in the process now of conducting these manual evaluations, and so hopefully in a few months we'll have some interesting results to share. Okay, so before we go into the Q&A, I just wanted to kind of share some of the kind of key takeaways from this research. First, we see that large language models can indeed perform extraction to a certain degree, but the evaluation part can be difficult. At least automatic evaluation can be difficult, and so as of now, the best way to evaluate these models for extraction tasks is just to do manual evaluation. That, of course, has the problem of not really scaling and not allowing for easily comparable to compare results across different approaches. We have been kind of toying with the idea of training models to conduct evaluation for extraction tasks. We have some preliminary, perhaps encouraging results, but we are kind of still working on this idea a little bit better. Another key takeaway is that small language models and open source language models can be competitive with larger proprietary models, which is very encouraging because relying on kind of closed source proprietary models is not ideal, and especially because we have to pay to access those. Another concern on using models like GPT-3 and 4 is that there is some evidence that these models have seen a lot of the training and a lot of the data sets that we use in NLP, which makes it difficult to evaluate their performance because they have seen the data. And so I'm very excited that the research in kind of alternatives, open source models is pretty vibrant. And yeah, look forward to see where this path will take us and what kind of developments can we foresee for these types of technologies. I'd like to thank you for your time, and I'll be happy to answer questions from the audience.
Thank you, Silvio. We have received a long list of questions, so we're going to head directly into the Q&A. So Silvio, the first question is from Ian, and Ian asks, can LLMs be trusted for real-time generative text in patient-facing medical apps? And what research is needed to build this trust?
Right, thank you. That's a very good question. So on the topic of trust, so I think that by themselves these models are prone to make factual errors. They can hallucinate, and so in order to build trust, we need to make sure that if the model is generating information about a patient based on their clinical notes, we would like to be able to link back to the evidence of those assertions. And so I think that kind of the line of inquiry that I just talked about today is one way to address this, where we are interested in models that can do both extraction and can do abstractive generation. And so if the model suggests something, we can always ask it to kind of link back to the original data. So basically, being able to verify the work of the model, I think it's critical to build trust.
Thank you. Jordana sent a question. What excites you and scares you about AI in healthcare?
Well, what scares me is the fact that these models can really sound authoritative, and yet at the same time they can make really subtle mistakes. And so linking back to the topic of trust, if we develop a blind trust in these models, at least as they stand today. This is quite problematic because, again, they can make very subtle mistakes. And so if the model is asked to generate a really long, say, summary of the conditions of a patient, and in the middle of all those sentences, small errors are made, and then those data are used to kind of inform decisions. I think it's quite problematic, and I guess that case of the lawyer kind of speaks to that. Probably the whole document that ChatGPT generated was looking good, but it didn't go and verify all the references and citations that the model generated, and that was quite problematic. So what excites me is the prospect of having healthcare by having experts being assisted by these powerful technologies. I think that these models can help at least have the potential to also help to reduce biases that the doctors may have. For example, diagnosis biases. Doctors sometimes have like these conditions that they are really keen on trying to find, and so having the ability of validating these diagnoses, having kind of a companion with whom they can with which doctors can kind of debate potential diagnosis, and having a conversation back and forth. I think it can help improve the quality of healthcare, and can also hopefully help reduce biases.
All right, thank you for that. Helen sent a question. Do you see the limitations of LLM in understanding EMR data, particularly in biased data of certain population?
Yeah, there's definitely that potential. Indeed, there's recent research showing that the way in which physicians and nurses write clinical notes, the language that they use leaks information about the race of a patient. And so there's this experiment where researchers took clinical notes from patients. They redacted the tokens that reveal the race of a patient, things like African American, Black, and white. They redacted all these indicators, and then they train a model, and even a simple model, which is a linear model, to predict the race. And they found that the model is very accurate, even when these race indicators are redacted. They then proceeded to remove all the tokens that were most predictive of race, and they found that the model is still able to predict race with fairly high accuracy, AUC in this case, which basically shows that the information about the race of a patient is deeply embedded in the notes. And if we combine this with the fact that different groups of people have received different types of treatments, we can see how if we just train models on top of this data, they can essentially perpetuate or amplify differential treatments in medical scenarios. And so that is quite problematic. And so on the other hand, I think that it's still not clear how much of these types of biases we can actually mitigate, because if we train models from data that contains biases, the models are trained to kind of replicate the data, and so it becomes quite difficult to do. Indeed, research on kind of debiasing models has shown that it's possible to kind of hide and mask the biases to a certain degree with some techniques, but ultimately it's always possible to kind of recover that information.
Great. We will go to Vikesh. Vikesh sends a question. Do you have any experience with using MedPalm 2? And if so, what are your thoughts about its effectiveness and what use cases does it do well or bad in?
Right. I don't have experience using MedPalm 2 because it's closed source. I don't think there's an API for it yet. What I do know is that the model was trained to on a lot of question answer pairs and medical exams, and so the model is really good and the model was shown to be able to pass the license exam. There is some, I mean, the only thing I know is from the paper. It turns out that, at least according to the paper, the model can make good recommendations for treatments that are as good as, or almost as good as medical professionals. So it's unclear, for example, how well will the model work on these types of use cases for retrieving evidence for diagnosis, for example.
Yuwandi asks, since diagnosis errors could be fatal, what are the techniques in this model to minimize the errors it generates?
Good question. So again, going back to this idea of empowering and not replacing human experts. So I think instead of trying to make sure that these models can perform their absolute best without any type of supervision, I believe that a better approach is to use these models to find information that will allow the doctors to make those decisions themselves. So yeah, my answer would be, let us find approaches where the models are actually working in tandem with doctors, but ultimately the doctors are the ones that make the final decision.
Okay, this next one comes from one of your students, I believe, Amir, from Zenas. Professor Amir, besides augmenting the prompts with known risk factors, what other ways do you think may be promising for getting the model to retrieve more specific evidence as opposed to generic evidence?
Yeah, good question. So one of the things that we are trying now is to take the model that we have been using, which is FLANT-5, and what we're doing is trying to fine-tune this model with medical data, specifically Q&A data sets. And the hope is that this will expose the model to more domain-specific knowledge. And the area of fine-tuning large language model is also evolving quite rapidly, with approaches that try to fine-tune these models by changing only a small number of the parameters. These are known as parameter efficient fine-tuning strategies. And so we are experimenting with those to see if we can get kind of more domain-specific, in this case, medical knowledge into the model.
All right, thank you. I think we have time for one or two more. From Shashant, can semi-supervised / shadow mode model deployment help with gaining gradual trust?
Can you repeat the question?
Sure.
Shadow mode model? I'm not sure if I know.
That's okay. I don't, that's what it says. But we are also going to be responding to some of these questions through a blog post. So I'll skip that one for now until we understand. Divya asks, how can we access some health data to start working on validating the information generated by LLMs?
Yeah, so there's not a lot of medical data easily available for privacy reasons. The main data set that we use that is large enough to experiment with machine learning approaches is called Mimic, and it consists of EHR data from the Beth Israel Deaconess Hospital, and that is kind of the main data set that we use for this type of research. It is publicly available, but you have to sign an agreement. You have to do first you have to do a tutorial on data privacy, and then you have to do this training, and then you need to sign this agreement so that you can use the model.
Okay, we're going to take one last question from Helen. Is it possible to combine LLM with structured data from EMR, such as lab results in your sepsis example, to increase accuracy?
Yes, yes, it is possible. However, it's unclear how much one would gain from that. And I say this because prior work, even prior to large language models, when people start to look at applying NLP to clinical notes, people found that if you have the clinical notes themselves and you combine it with these lab results, you get a certain performance. But if you just use the clinical notes, you get about the same level of performance. And so if you have access to the notes, the lab results themselves are somewhat redundant.
Thank you, Silvio. That's about all the time we have for Q&A. So I want to thank you for this very timely and thoughtful expeditions and experiential AI discussion. For those listening, Silvio's full talk and slides will be published on our website shortly. We will also publish a blog post containing Silvio's answers to audience questions that we didn't get to, as I mentioned before. Please join us for our next webinar, Sensing and AI Ethics, Applications in Health, coming up on Friday, June 9th at 2 p.m. Eastern Standard Time. We also invite you to subscribe to our newsletter in the AI Loop. You can find events, newsletter sign up, social media links, articles, and more about our work at our website, ai.northeastern.edu. Thank you for joining us and have a great day.